start. It's my great pleasure to be here. Thanks for inviting me. And as a part of my visit, I'll be teaching this graduate course. Some of you will get it for credit, some of you just auditing it. So all great, all fine. And some people will join online. I guess we'll see how that will work. Well, most of the things I will try to put on slides, but some derivations and some clarifications I will use board for. Hopefully people online will see it. Well, now this is kind of the course that is supposed to be graduate course. And in my mind, the main difference between graduate and undergraduate is graduate is more or closer to what the state of the art currently is. And the idea here is maybe not to go in detailed derivation everywhere, but rather give you some ideas about the problems, some ideas what is interesting, and so that you could maybe read more in your free time and learn on your own. And if I could stimulate that have some questions about the subject, that is the main point, actually, because in science, you kind of realize that having questions is more important than answers. And that's how you kind of start essentially developing the new things. All right, so let me then, yeah, I am recording this. How do we see it? I think because I pressed. Oops.
Just to be sure.
Oh, stop recording. Yes, so it is recording. You see?
Okay.
Right, so resume. Okay, great. Cool. And people online, I guess, since we don't have too many, I encourage you asking questions just without raising hands, just speak up and I'll try to address. So I kind of highly appreciate if people ask questions. I won't worry too much about the time. We'll see how far we'll be able to go. But some form of dialogue would be very nice, because also I'm not sure what's the level of the audience, right? So so I have some assumptions which may not be always correct. All right, so what this course will be about is essentially how to develop new algorithms for quantum computers to solve quantum chemistry problems. All right, and this is essentially the problem, time-independent Schrödinger equation for the electronic Hamiltonian. And before we dwell into, I guess I have a slide with a few more things. Some of them are organizational, some of them are more about the course. So I guess my background is quantum chemistry in general sense. I did some developments of electronic structure and quantum dynamics for quantum and classical computers. What these lectures will be about quantum algorithms for NISQ, near intermediate scale quantum computers without error correction. And also in the second part of this course, we'll try to cover fault-tolerant algorithms, the algorithms that assume some error correction. Okay, and mostly these algorithms will be for the gate-based quantum computers, as opposed to some other computer technology, quantum computing technologies like adiabatic analog quantum computing, for example, right? Also, there are some techniques, so-called measurement-based and annealing. So I am not gonna cover them extensively. Maybe we'll have time at the end. And other important topics that will probably not be covered is various architectures for qubits, because it's hardware, it's not the area of my expertise, and I could just point out on some sources where you could learn about the hardware, and of course there are very many approaches. No one exactly know for now which one will prevail, but one of the major, I guess, hardware is a superconducting hardware that Google and IBM is developing, and I mostly were thinking about those kind of qubits when I was preparing and thinking about the algorithms. So those who will be taking this course for credits, there will be exercises and some reading materials for, I guess, reading materials will be for everybody. And depending on your, again, background, some of the reading materials you may already be very well aware of. And after lectures, I will try to put it on, I put here Google Doc, link will be distributed, but if we have a Slack channel, then I'll put it there, right? And just to, for me to check your homeworks. By the way, how many people are taken here for credit? Could you raise your hands? Okay, quite a bit. All right. So
there are also few online.
Few online. Okay. So about 10, 12.
10.
Yeah. Okay. All right. Yeah. So I guess then I will just receive the scans of your work on my Gmail address to make it simple and private. So you could send them into that address. Okay. All right. Now, here there are a few first topics that that's mainly probably what we'll be covering this week. Yeah, so like hopefully we'll see whether we'll get to the topic number 3, but I will start with electronic structure problem. And I assume here most of you are chemists, right? And probably heard about electronic structure problem. We will talk about second quantization and how do we get from fermions to qubits, and a few other topics which are mainly referring to the near-term algorithms. I guess the key notion in terms of algorithms will be variation of quantum eigensolver, which some of you may have heard. But well, we'll be considering some of the aspects of that framework, because it's really not an algorithm, but rather framework within which you can do lots of interesting developments. Okay. All right. With this plan in mind, I periodically will post some of the textbooks where you could learn more, because I won't be able to cover everything that is needed. Let's say second quantization that we'll be talking about. It's discussed in Hilgacher's book, the one on the right, and very well. And of course, I will just cover some few details that just allows us to establish the framework in order to talk about things. And other things you could read more extensively in those sources. All right, so starting while we're doing this, we are interested in essentially describing molecules, either for various sorts of purposes, technological use of molecules. Of course, you probably heard about the catalyst, the drugs, cell phones, the screens of our devices, right? And in order to kind of make this process of finding new, better candidates for those solving those problems, we sort of want to describe the property of the molecules accurately, and more accurately we can describe them on a computer, then less trial and error we need to do in the lab, right? So that's the kind of the basic idea. And electrons and nuclei, those are the main particles that we need to describe. And that's we don't go into the nuclei. So for us, electrons and nuclei is kind of elementary particles. Okay, and in order to get to the electronic structure problem, we just need to, I guess, separate electrons from nuclei. Okay, you don't see my mouse. Let me just try to this thing maybe down. Okay. Yeah. All right. Okay, so very simply, if we talk about any quantum system. In general, if it's isolated, right? Then we could describe it using everything we want about it, using time-dependent Schrödinger equation, right? Written here. So the small r is a collection of electronic coordinates, big r is a collection of nuclear coordinates, and sort of that's our sort of framework. Now it's applicable only if it's we have isolated case and we have non-relativistic systems. Now, the methods that I'll be describing in this course potentially could be generalized to even relativistic cases, but we mostly will be having in mind the Hamiltonians that are coming from the non-relativistic theory, okay, for now. And then if you actually can solve time-independent version of this equation, then you could go back and solve the time-dependent. So the relation here is very straightforward because the systems that we're dealing with, they, like molecules essentially, they have time-independent Hamiltonians, and therefore to solve time-dependent problem, you could just focus on time-independent, and then take the time-independent equation solutions and put them in this expression. You could easily check that will solve the time-dependent equation, assuming that you put the right initial conditions. So if time is 0 here, then your wave function needs coefficients here. They need to be selected so that you start with the right wave function. All right, so this is all to say that we could now focus on time-independent Schrödinger equation, and only, I guess, case where this may not be applicable is when we have strong fields that are time-dependent, and this could be part of the kind of spectroscopic investigation, but usually in the normal spectroscopy, not too strong field spectroscopy, you could sort of assume that the field is perturbation and get back to the essentially solving time-independent problem. All right, so then what's the issue with this problem? Generally, there is so-called curse of dimensionality in quantum mechanics, because even if we consider, say, hydrogen molecule, 2 electrons, 2 nuclei, right? So the wave function, even if you have that wave function specified on the grid, someone already solved the equation for you and gave you the function, then you could easily see that it's 12-dimensional object. And if you have 10 even points per dimension, then you have trillions of points to essentially store for such simple system. And of course, if you go to the larger molecules like proteins, then number becomes astronomical. And of course, origin of that is the the number of dimensions goes into the exponent essentially, right? So the quantum mechanics is exponentially hard because the objects that we are working is the wave functions, and there with dimensionality, the amount of information grows sort of in this straightforward realization exponential, right? And so something needs to be done about that. Now, electrons and nuclei, they are not created equal, and Born and Oppenheimer sort of figured that out, or figured out the way to use that fact to our advantage. So they created this Born-Oppenheimer approximation, which you probably heard about. So the idea is that we could freeze some variables, and that makes wave function simpler because some variables now become parameters. And in the Hamiltonian that we are dealing with in molecules, we have just essentially kinetic energies and potential Coulomb interaction between the particles since they are charged, right? So they figured out that it's good to freeze the nuclei and consider a smaller Hamiltonian, which is the electronic Hamiltonian underscored there, right? And the idea is that we keep the nuclei in the mix, but we keep them frozen. All right, and this was very productive because it gave us the so-called sort electronic Hamiltonian eigenvalue problem with the parametric dependence on nuclei. So we can change the nuclei and solve for the electrons first. And then these eigenvalues of this eigenvalue problem provide the, so we love the biochemist potential energy surfaces from which you can derive the spectroscopic parameters for the, say, diatomic molecules, or look at the chemical reactions. And even though it seems like a very kind of reduced part of the overall problem, because it turns out that the electronic energy scale is dominant in general, then if you solve that problem and see that in order to go from one configuration to another, you need to have you need to go over quite a large barrier, then you could estimate roughly what's the kinetic energy. What is the need for the temperature in your system, so that the reaction could go with a significant rate, right? Or it won't be able to essentially proceed. So therefore, even from this very reduced representation, we could still learn a lot, and that's why chemists like potential energy surfaces. Now, I wanted to, I guess, explain a little bit more the Born-Oppenheimer approximation here, and what I actually like to call it more like a separation of electrons and nuclei, because even when you read quantum computing literature, people sometimes claim, okay, well, the electronic problem is an approximation, right? But in reality, it's just a part of the problem from where you can build the full the solution of the full problem. And let's just I guess consider it a little bit deeper. So again, the same sort of idea. We try to formulate electronic Hamiltonian following Born and Oppenheimer. But what's kind of the, I guess, the rationale here? Usual textbook statement is electrons are 1,000 times lighter than nuclei, so they're much faster. Therefore, it's okay to freeze the nuclei. Okay, so we all probably heard this phrase once or several times, and then they essentially do this factorization of the wave function, taking the electronic times the nuclear, and then after solving for electronic, they formulate the equation by projection to the nuclear space. Now, I want to kind of pause a little bit and ask what does this really mean? Electrons are much faster than nuclei. They are not classical objects, right? So how do we really judge whether this is right or wrong, right? So it sounds right because the masses are indeed, the ratio between the mass of electrons and nuclei is indeed 1,000 times. But in quantum world, how can we say that something is faster than one object is faster than another object, right? How do we make things move? And well, my statement here that there are different ways to think about movement in quantum mechanics. Well, one, of course, is kinetic energy, right? So you could look at kinetic energy and see whether kinetic energy is large or small, or momentum, and those two things actually do not correspond to each other very well in like quantum mechanics than compared to classical mechanics, right? So if we even think about, say, particle in a box and the ground state or excited state of particle in the box, the kinetic energy, which is the entire Hamiltonian, right? So with boundary conditions, so kinetic energy will be non-zero for any of these states, while the momentum, let's say, operator will be zero for any of these states. So that's clearly already here we could see that quantum thinking about the movement of particles is quite different than classical, right? Because T is just proportional to P square. So P square is non-zero, but P is zero. And actually for any state that is real, expectation value of momentum is zero. And what I'm saying here is that only superpositions are moving in quantum mechanics. What I mean by that is that Okay, so in order to think about the movement in the one way to think about the movement in the classical sense is to prepare the wave function. And since wave function is the object that we cannot observe, but the probability density is the object that we can observe, see if the probability density is some function essentially depends on time or not, right? So, and if you take any state that is a stationary state, well, then its probability density will be something like this, right? And absolute square is not, it's essentially constant in time. Constant in time. Right? So very simply, if you just look at the what's going to happen if you have a superposition, you have two states, both let's say have energy phases, then a probability density will depend on time because of these cross terms, right? Coherences, essentially. And it will move in space like the probability density of the particle. It's the same way in the classical physics, we will think about moving object is, I look at the object, is it here? And where is it in a different moment of time, right? So we could see that the larger the energy difference in that superposition, the faster the movement will happen, essentially, right? And this is more reasonable, I guess, or quantum view of what the movement is. And considering that, you could also think about electrons and nuclei, because essentially what it boils down to is that the energy scale of electrons is much larger than the energy scale of nuclei. All right, so that's how this sentence about the what is faster, what is slower could be interpreted in the quantum correct language in a sense, right? Because the energy differences between the electronic eigenstates here, they're usually way larger than the energy differences that you obtain from the nuclear equation, okay? And that's what was driving sort of force behind the Born-Oppenheimer separation. There is yet another interesting aspect of this problem, because here we have problem of essentially two types of variables, small r and big R. And from the physics point of view, one can solve this this ansatz that Born and Oppenheimer suggested. That's a product, but this function comes not from the electronic, not from the pure electronic Hamiltonian, but electronic Hamiltonian with frozen nuclei, right? So that is a little bit strange in general from the many body physics point of view, because we decided to freeze some variables instead of just kind of accounting for the coupling between electrons and nuclei. So one could potentially do is take the electrons, solve for the electrons, and then solve for the nuclei, and then account for the electron-nuclear coupling, right? So that is one way that probably you've seen in the quantum mechanics solving the problems, multiple particles. And here it won't work. And there is a simple reason why it won't sort of work practically here. Could you sort of guess what would be the result if we solve for the electrons first, for the nuclei, right? So our Hamiltonian in general has the kinetic energy of electrons, electron repulsion plus then the nuclear part. Same thing here. And then we'll have electron-nuclear coupling, right? So what if we just solve for this, and then form the wave function as a linear combination of some sort of eigenstates for this Hamiltonian, right? So with some coefficients.
The electrons are unbound.
Right, right. So essentially, solving this problem and this problem separately will generate the solutions which are really far from the solution of the molecular problem, right? Because we know molecules are compact objects, right? And when we ignore electron nuclear attraction, electrons will just fly away. It's going to be plane waves. Nuclei will fly away from each other, right? And you will be governing the solution of the total problem using infinite number. You can do that conceptually, you can do it, but the sum will need to go over infinite number of essentially terms just to get something compact out of the very distributed or very delocalized states, right? That's why it's not a good idea. That's why Born-Oppenheimer's suggestion is actually, well, very, very insightful, right? So it's not though anything weird. All you do is just instead of producing electronic functions from the only electronic part, you also include the electron nuclear attraction, right? So you freeze the nuclei for a moment, and the purpose of that is to keep the electronic functions sort of compact, all right? Now, to illustrate this, I couldn't resist to make it really trying to make this concept very simple. But one can use Born-Oppenheimer even for problems like particle in the box, right? So the way to illustrate that would be, let's say, if we have a two-dimensional box, but with the infinite walls, and then one wall is so the one dimension is much larger than another, right? So why is done this way? Because for uncoupled problem, where if we ignore the dxy for a moment, the coupling between x and y coordinate, we all know for a particle in the box, these are energy levels, right? And the dimension of the box goes into the denominator, so we square. So in order to simulate this idea that electron energy scale is way bigger than scale of the nuclei, we could make a dimension of one side 44 times larger than another. So the short ones will correspond to the electronic variables, the large long ones for the nuclear variables, and that would account for the mass difference, because for the hydrogen versus electron, the mass difference is like 2,000 times, right? So that if you take square root of that, it's going to be 44. All right. Now you could solve this problem in a naive way, non-Born-Oppenheimer way, where you solve for the for the eigenstates of x, eigenstate of y, and then combine them together, right? So this is the wave function ansatz. Okay, have a products all possible with coefficients. Of course, numerically you would formulate this as a sort of matrix problem for the coefficients, but the functions you obtain from the uncoupled problems, which are, we know, is particle in the box, right? And then it turns out you could do this at home with alpha, which is relatively small, 0 minus 0.1. The alpha is a strength of the coupling. Then there are only 80 terms needed to, let's say, get to the fourth digit after. It's a completely arbitrary choice, but to calculate ground state energy to the fourth digit, you need 80 terms in this linear expansion, 20 terms along one coordinate and four terms along another coordinate, right, I and j. All right, so then alternative expansion, alternative way of looking at this expansion, more closer to the Born-Oppenheimer way, would be, we could always write this in terms of just a single index, where we kind of define the sky part as a sum over the second index and the second functions. And that is the reason why, well, this is kind of another wide way of writing things. Just will be more related more to what we are doing in the Born-Oppenheimer treatment of the same problem. Now, in kind of the Born-Oppenheimer way, what could do is to write now the wave function in sum in a sum of these products, where one function phi I will be defined using, let's say now, instead of just h of x, it will be h of x plus the coupling, right? But the y coordinate is frozen, so it's fixed as a parameter, right? And we still can solve. It's not going to be, these functions are not going to be eigenfunctions of particle in the box anymore. They will have a kind of extra complexity, but we still can solve this as a one-dimensional problem, right? So y is just a parameter. Okay, it's going to be essentially in one dimension particle in the box with the kind of level at the bottom, which has a kind of the angle to it, right? And so you could do that, finding these phi functions, which are analogs of electronic functions, and doing some approximations which correspond to the Born-Oppenheimer approximation. And what the approximation really is that when you are trying to find the equations for the chi part, you are ignoring the action of the second H2 part, the kind of the nuclear Hamiltonian sort of part, on these functions that you found, because they parametrically depend on y. So potentially you should be able to, well, consider this a dependence, but you're ignoring it, thinking that it's small. And then you could formulate for equations for chi, ignoring that dependence. That would be exactly Born-Oppenheimer approximation. And it turns out that this approximation for this problem gives you, with only a single term, which is like the Born-Oppenheimer product, it recovers the ground state energy with the right energy value, right, up to the fourth digit. And you don't need 80 terms to do this, right? So this is a simple illustration where you could use the Born and Oppenheimer trick in other many-body problems. For that, you freeze one coordinate. If the coupling is strong and you cannot sometimes ignore it, you could just freeze the coordinate and obtain the solution for a single variable, and then use it in the ansatz, like Born-Oppenheimer ansatz. Okay. All right, so then you could go and do the dynamics with this. The Born-Oppenheimer dynamics generally works for time-dependent, the same way. Earlier I said that we could just solve the time-independent and then go back to the time-dependent. But there are more efficient ways where you just solve the electronic problem and then formulate what the nuclear wave function will be for as a solution for time-dependent part, assuming that you can ignore other states, other electronic states. Okay, and this is what essentially Born-Oppenheimer chemical dynamics is. Michael Polanyi, I guess, back in the beginning of 20th century, formulated this activated complex theory. So to kind of see the chemical reactions rate, and then you could confirm this rate by essentially simulating this time-dependent part. But the essential ingredient is, of course, the electronic potential energy surfaces, right? You need to get them right, and then the dynamics will be correct. Or you could skip the dynamics by just using Arrhenius theory and assuming certain things about I guess the barrier needs to be large enough so that there's an equilibration in the system. At the chemical reaction rate depends strongly on the accuracy of your potential energy surface barrier, right? And you will see, if you look at the kind of quantum computing literature, people very frequently try to simulate things up to 1 kcal per mole and cite this as a chemical accuracy in potential energy surface. And the reason for that exactly comes from the activated complex theory, right? Because what 1 kcal per mole is if you put in the ambient like in room temperature conditions, if your energy is accurate up to plus minus 1 kcal per mole, then your reaction rate for the room temperature will be of less than an order of magnitude. Okay, and that is considered to be okay. Now, this is the reason why this number is so frequently used. All right, so then, of course, if you know potential energy surface, you could formulate, look for catalysts that reduce the barrier, right? And that's one reason why we are trying to model chemistry. But sometimes we need to go beyond a single surface situations. And one simple example is this molecule, rhodopsin. It's actually the reason why you can all see me today, right? So currently, as we speak, the vision process is happening, and it involves more than a single state, right? But and that's where Born-Oppenheimer approximation breaks down. There's a very famous conical intersection situation. Now, what happens in this molecule is there is a first step in the vision process that involves transformation in the retinal chromophore from the cis to trans. And the way it happens is the light comes in. That's why we can see only when there's a light, right? And the transition over this barrier happens because first system goes to the excited state and then eventually ends up in the ground state, but behind the barrier already, all right? And in order to describe that, well, if you zoom in closer to where the surfaces come close to each other, there is this potential energy surface feature called conical intersections, where it allows the system to kind of essentially the energy scale of electrons and energy scale of the nuclei become very close, and there are possible transitions. And then you sort of, to describe the dynamics well, you need to have at least presence on the multiple surfaces. And the wave function ansatz become electronic states, and then nuclear wave packets, nuclear wave functions describing where the system is present on the different states. Okay. Now, of course, if you are able to solve the electronic problem, then you get the electronic states for this ansatz, and you can solve for the electronic states separately. You don't need to solve for them all at the same time. In that sense, Born-Oppenheimer separation can be used here as well, and it's this is where you could see how it builds up the big solution for the bigger problem, right? Even beyond Born-Oppenheimer approximation, and the formalism works more or less the same way. You start with time-dependent Schrödinger equation, put this ansatz again, where phi i's are electronic functions, and they are eigenstates of the electronic Hamiltonian, the one that actually involves the electronuclear attraction, right? And by doing some algebra, since we know the phi i's and we know their properties, that they're eigenstate of electronic Hamiltonian, they are orthogonal, then following this sort of algebra, the left-hand side could be considered. And I will, of course, provide the slides so you don't need to really memorize all that. Essentially, what you get is the equation for the nuclear part that drives the dynamics. And these equations, they are they're different from Born-Oppenheimer approximation by these terms that couple different surfaces, right? So tau ij, these are the terms. If you look closely, they essentially describe how the electronic function depend on the nuclear coordinates. Okay, so the more the electronic functions depend on the nuclear coordinates, the larger these terms are, right? Because they involve this so-called derivative couplings. And that's the reason why Born-Oppenheimer approximation breaks down, why you need to go beyond a single surface. When these couplings become large, they promote essentially the transitions. And here's a very simple example to avoid abstraction for just two states. It turns out if you project the equations in just two states are involved, like in case of rhodopsin, then the the formulation becomes like written there, right? And then one can just for getting some intuition, consider, let's say, first order couplings, right? And how big are the first order coupling? How to know when are they big and when are they small, right? So it turns out that all you can do is here to get some intuition is you could differentiate this matrix element, right, which is 0 to start with, because electronic Hamiltonian, it's the operator that is the phi1 and phi2 are eigenstates, right? So once you act with the electronic Hamiltonian to phi2, you get energy and phi2 back, and then phi1 and phi2 are orthogonal, so you essentially differentiate in 0. And then, but that is great because you could differentiate 3 parts inside of this 0, and you get these extra elements, which none of them are 0 by itself, but together they are 0, right? And what this allows us to do is to do a little bit more algebra, get kind of the expectation value, eigenvalues of the electronic Hamiltonian, right? Out of these two, right? And using the fact that the electronic Hamiltonian is Hermitian, then you could move 2 of these terms to one side and get this ratio, which essentially gives us this intuition that the smaller the energy difference between the states, the larger the coupling, right? So that's the basic idea, right? So this term, I don't know, like some value which is not necessarily 0. And then you could see that if the situation is like a conical intersection case where the surfaces come close and even touch each other, right? This becomes 0, and the non-adiabatic couplings become infinite, right? So clearly you cannot use a single surface dynamics or single surface consideration in these cases. But you still can sort of obtain the still electronic structure calculations will be still useful, right? Because you're getting all the components to build the right equations involving multiple states. Okay. Now the last point here, why conical intersections are so ubiquitous. You could actually do. I would even claim that they are as ubiquitous in the case of like as the harmonic oscillator approximation, right? In the case of a single surface, when we are dealing with a nuclear kind of situation where we have we already solved the electronic structure problem. We have Tn plus electronic energy depends on R, and then there's a chi equals to E pi, right? So why we very frequently use harmonic oscillator problem, a harmonic approximation to this problem, because we are starting in the minimum, right? Minimum, if we expand this function of the potential essentially, and the minimum first derivative is 0. So the only first non-trivial part, this problem is quadratic, right? So that's why it's very natural to use quadratic approximation. It may not be like always accurate, but at least this is the kind of the first thing that comes to mind in this problem. Now, in case of intersections or in case of multiple states, it turns out that kind of when the surfaces come close to each other, the so-called conical intersections, they are as frequent as essentially quadratic potentials, because one can simply write the electronic Hamiltonian in terms of as a sort of operator in terms of states that are obtained only on a particular R0 some nuclear configuration, and then do the expansion of the electronic Hamiltonian in the different points. And it turns out that that expansion has the first term, which is linear, which is no surprise, right? Because first non-trivial term in any expansion using Taylor series will be linear. And then because here we use a bit of a symmetry argument that the states that different in diagonal energy, like the differences in the diagonal terms, they are usually driven by one coordinate, and this the difference in the off-diagonal terms are driven by another coordinate. Then we could simplify the situation to just having the two-dimensional case where x and y are just two types of nuclear coordinates. And if you diagonalize that matrix, because that's what we do in order to go to the adiabatic picture, then you get this well, square roots, and they are for, essentially equations for the cones, right? So then the cones become just from diagonalization of these terms. And the two CI conditions that in order to have conical intersections is that the diagonal elements in this matrix, they eventually need to be zero, which is a kind of possible when x and y are zeros, and the off-diagonal couplings are also zeros, right? And so these two conditions could be satisfied when you change the nuclear coordinate. So if you have n dimensions, let's say in water molecule, you have 3 internal coordinates, and n-2 will be the subspace where you can satisfy 2 of these conditions, which will be one-dimensional. But even in larger molecules like proteins, if you have thousands of degrees of freedom, it's really easy to satisfy these 2 conditions, and that's why intersections are very, very frequent. Now, they're actually more frequent than sort of avoided crossings, because in case of avoided crossing, if you have 2 states, in order to have avoided crossing, formally, you need to have this gap minimum. And the condition for the minimum is that you need to have n nuclear derivatives to be 0. So that's more conditions than just 2 for the conical intersections of 2 states. Of course, if you want to intersect more than 2 states, then it will be more conditions there, more kind of harder to satisfy. But for the 2 states, it's relatively easy to find those intersections in large molecules. Okay, to summarize, so quantum chemistry in very strict terms, it's just electronic structure problem. Very frequently, it's perceived as like, okay, it's just Born-Oppenheimer approximation. I like to say this is more like of probably a separation that we are doing and solving the part of the problem that can be then used in the larger problem for the total either dynamics or spectrum of the molecules, right? And we're getting the functions and getting its properties. Now we are solving in the electronic structure problem parametrically dependent eigenvalue problem that is exponentially hard unless you do other approximations, because it's just with the number of variables we still getting effectively a very difficult problem, and that's one of the reasons why people think hopefully that quantum computers could make a difference here. And now, as I said, for many chemical problems, electronic structure can be just the hardest part, and it's like its accuracy will determine the accuracy of the rest of the modeling. And for molecules, the reason it could be the hardest part is because the nuclei really are less quantum, since they have larger masses, and very frequently they are simulated quite successfully using classical dynamics, right? So for electrons, it's really hard to simulate them classically accurately. Okay. Any questions so far? Online people? All right, then we could go to the second quantization.
Maybe we could have a little break.
Yeah. So,
And,
okay, yeah, let's do a 5-minute break or a few-minute break, and yeah, reconvene.
usually
Okay.
told not to go beyond 3/4 of an hour in a row.
Okay, yeah.
So
Good
people
point.
could keep.
Good point. How long are you staying at it? It was mid of September. Yeah.
I think it's just.
Oh, that's for
All right. So let's continue. And the second point, second quantization. And the reason I start talking about second quantization, because second quantization, as you will see, gives a very easy way to connect electronic structure problem to eigenvalue problem using the, instead of fermionic degrees of freedom, qubit degrees of freedom. There are formulations that I use in first quantization, but they're more complicated. So we don't start with them, surprisingly. And maybe if the time will permit, I will cover them later. But there are some developments that I use in first quantization, and they have some benefits. But conceptually, it's much easier to understand the second quantization and its connection with quantum computing. Now, there is this literature. If you are new to second quantization, I highly recommend Hilgaker's book, and it covers, and not only covers the second quantization, but it also systematically uses in all branches, almost all branches of classical quantum theory. And these are on the right, more physical books. Okay, so now we talked about electronic structure in the first quantization terms, and yeah, we have still like electronic variables, nuclear parameters, and yeah, these are just expressions for the terms of the Hamiltonian. I prefer to write them in the atomic units, where constants are essentially, many constants could be just substituted by ones. And the problem, one can say, is still that even if we separated the nuclei, we still have curse of dimensionality, because we have electronic variables, and with larger systems, the number will grow, and it will go into the exponential factor, right? So now, what chemists usually do in this case is they take the n electron problem and produce the one electron picture, one electron basis. So they essentially represent the electronic function as potentially products of the electronic states for single electrons obtained from somewhere. If we skip the R dependence, the nuclear dependence, usually these molecular orbitals that you are, as chemists, all familiar, they could come from Hartree-Fock theory, mean field theory, or DFT sometimes, right? So it's not that hard to generate them, and they assume certain simplifications in order to certain independence of electrons in this kind of system, but it's just for the sake of just generating good functions, simpler than going after all the multi-electron wave functions. But because the electrons are fermions, we need to satisfy the not anti-commutativity, but anti-symmetry, right? So when we change the coordinates of the multi-electron function, any2, then you get the minus sign. And the two electron example here is if you have the two electron function written as some kind of products, which the most natural construction to account for this sign change is Slater determinants. So for any two electron function, you could write it as a linear combination of essentially Slater determinants, the psi functions, right? Where could be written like this. So as you all know, we sort of start with one electron functions and obtain this many Slater determinants for using the one electron functions, right? And now, yeah, these Slater determinants, they have okay, essentially minus sign when we change the coordinate system, and that since all of them have that, we have a total wave function written as a linear combination of them that sign change. And more generally, we could now go into the second quantized form of theory, where Slater determinants are used as basis functions, right? So these are our one electron states, but also for second quantized form, it's convenient, instead of writing every time the Slater determinants like this, like a determinant of the matrix, to write them as just a string of numbers, and the numbers are simple zeros and ones, right? So we're assuming that we have so this one electron functions from 1 to m, and then if the Slater determinant contains a particular spin, we call them spin orbits, right? Because they have a spatial part, let's say for the electron, and then the spin part could be alpha and beta, since electrons have spins, right? So the spin orbits, they are either occupied, they are part of the Slater determinant, or unoccupied if this say first or spin orbit is occupied, then we put 1. If let's say second one unoccupied, we put 0, and so on and so forth. So we can really write so-called occupation number vector, and that will be completely equivalent to essentially specifying the Slater determinant that we're working with, right? And so these functions you could find, like, they form a space, and it's a linear space, so equipped with the inner product, because you can actually take the inner product of individual spin orbits and then generalize it to inner products of the kind of the Slater determinants, right? And it's quite simple, because we're using no Slater determinants orthogonal system of orbitals, spin orbitals. Let's say if we have phi I spin orbit sigma I, and then phi j sigma j, then this is just delta ij, right? So, and then we could generalize this to the Slater determinant case is written, right? So all essentially the whole binary string of one state needs to be exactly the same as a binary string of another state for this inner product to be non-zero. And general vector in this space, as in any linear space, could be written as a linear combination of this state occupation number states. You could put the resolution of identity. So identity operator could be written like this. And then more generally speaking, we have a Fock space of m spin orbits. It's a direct sum of essentially qubit spaces that contain, let's say, a particular number of electrons. The number of electrons correspond to the number of ones in these strings, right? And m is fixed number of spin orbits, right? So here's a number of electrons defined as just a sum of all the Ks. They are either zeros or ones, so only ones contributing. And then what is a little bit maybe weird compared to the first quantization is this vacuum state. So the vacuum state is a single member of FM0, which is a string of zeros. Essentially, we don't have any occupations for all these spin orbits that we introduced. It's still a state that has non-zero Born, right? So vacuum with itself is 1, but it's just there for completeness of the power construction. Okay, and then another combinatorial or mathematical fact, which another, I guess, illustration of why problem, even if we don't look at the entire Fock space, but in the subspace of n electrons, so the, let's say, the number of dimensions in this subspace is m choose n, right? So it's like n factorial divided by n factorial divided by n factorial n minus n. So it's a huge number, and then if you sum them all, then it's 2 to the m. So that's the exponential dimensionality of the Fock space, right? Now I used word direct sum, and here's a simple question: what's the difference between direct sum and sum? Familiar with that notion? What do we mean by direct sum? Actually, it's a somewhat simpler notion than you probably have seen it a couple of places. Then just the sum. Yeah, you need to. If we're talking about sum of two vectors, then you need to know how to sum them, right? That will be a normal sum. But then if we have a direct sum of two vectors, or a direct sum of two matrices, let's say A plus B. So direct sum means we don't mix them, right? So this simply means it's like we have a pair and we keep them like apples and oranges separately. And in case of matrices, we talk about the block diagonal construction, where we again don't mix them, right? So Fock space is a direct sum of Hilbert spaces with a fixed number of electrons, so they don't mix, right? And that's why it's a sort of, it's like a compartmentalized construction, right? That is convenient, as it turns out, well, for our purpose. But right now it may look like excessive, right? Because if, for chemists, it looks very excessive and unnecessary formalism, because, well, when we're going after a particular molecule, we're interested in a particular number of electrons there, maybe plus minus 1 anion, cation, but yeah. All right, so now operate, like we talked about the states. Any state in this Fock space could be then written as a linear combination of the Slater determinants. And then we also need operators to work with this. And all operators can be built as polynomials of creation and annihilation operators. So there are building blocks, which are called creation and annihilation operators, and anything can be built out of them. That's a nice feature. So for the creation operator, many of you probably familiar, but let's just quickly review, is that what creation operator does, it takes the Slater determinant written as a string of numbers, right? And if it has an index, of course, where does it act? So it's AP creation. So it acts on the orbit, spin orbital, right? And if the spin orbital is 0, it creates 1. It flips it from 0 to 1. And if it's 1, then it kills the state. And what is important to kind of always keep in mind is that we're working with fermions, and those are, even though we're writing them now as strings, those are Slater determinants. And it turns out that, well, essentially the Slater determinants have this signs in front of the kind of, if you start changing the rows or columns, then because of that, effectively we get these extra factors that essentially signify the anti-symmetric nature of fermions. All right, and when the creation happens, then we need to put the factor that effectively you can think of it as a -1 for every occupied spin orbital before where we created the electron, or you could think of this as a -1 into the sum of all the occupations, right? Because there's products of -1s, interpret them in different ways. And now using this creation operators, so you could write any Slater determinant as a product of creation operators acting on the vacuum, right? So that's another simple formal thing. And one can do property derivations for these creation operators. One simple property is that, just following from the definition, is that if you apply creation operator twice, then you're going to get 0. And that will happen independently whether you applying it to a state where you can create or you cannot create. You cannot create twice for sure, right? So that's why you could write an operator expression where square of the creation operator is 0. In algebraic terms, this is called nilpotence, but is a kind of convenient property. And then turns out if you play a little bit more with algebra and look at what's happening if you creating on P spin orbit and Q spin orbit, and then do the different kind of order, since you could see that doing that in different order will give you 0, and you could kind of convince yourself doing this with I guess any generic state. And since it works for generic state, you could write them without the state, right? And the expression will be like this. And this is what we know as anti-commutator. Okay, so for the course, I will try to, since it's slides are taken from different sources. This one is particularly Helgacher, but sometimes the anti-commutator also will be as a curly bracket expression like this, and this is exactly the same as what was written there as this with plus, right? The commutator, on the other hand, is just this. Right? So this is going to be AB minus BA. And we'll be talking a lot about commutators and anti-commutators because they are all related to the eigenvalue problem. All right, so this is the one property. And then we can go and define annihilation operator. And for that, all we need is just to do a joint operation for the creation, right? So Hermitian adjoint operation. And because the creation and annihilation operators, they are not self-adjoint or Hermitian in general, then your A dagger is not the same as A, right? And that essentially by doing the Hermit conjugation, you get in a different operator. And the idea of that operator is quite opposite. If you have no electron on the p spin orbit, then it creates, again, respecting the fact that you need to think about the populations of previous spin orbits. All right, so then main properties also could be derived simply by taking the properties of creation, which we already saw, and do the Hermit conjugation. This will generate the properties of annihilation operator. And there is one more property that the annihilation operator will kill any vacuum state, which is just coming from the definition that if there's no electrons and vacuum has no electrons, then it's clearly will be always 0. Okay, So now one can combine some properties of creation and annihilation operators together, and combining that, if you apply them essentially one after another in different orders, you could see that essentially the anti-commutator of creation and annihilation operator gives you 1 instead of 0, and that can also you can check that if you have different indices, then the anti-commutator again is 0. Okay, and so that kind of combined gives you the basic algebra of creation annihilation operators, and this is very powerful algebra. We will look at the consequences of that in the future. I just don't want to, I guess, overload you too much with formalism, and in general, in this course, I will talk about abstract algebra constructions like groups, algebras, and linear spaces. We already talked, but I don't want to kind of, as following mathematical books where they give you a lot of material and no applications very frequently, especially like purely mathematical books. But here we will just see if there will be nice application, then we will talk about the mathematical structures. But this is generally called Clifford algebras, and because I also believe in the power of repetition, I don't expect you to kind of understand or memorize everything from the first time. So that's why I'll try to repeat myself somewhat. So just a little bit of I guess algebra in this case is that formally we use word algebra loosely, like whenever we just have addition, multiplication, subtraction, division, right? But formally we have well, we probably all were familiar with linear spaces as a construction, right? So the normal vectors, and in quantum mechanics give you another example of linear spaces where it's not a normal pointy arrows, it's now functions that we have as vectors, and then you can add them with some coefficients, right? And the nice thing about linear spaces, if you do this, then you get again vectors, right? So, and there are conditions on what you can do with these numbers. They're coming from the field, but essentially you could do pretty much anything you like. Usually we do with numbers, and vectors, on the other hand, we can only multiply by number and sum, right? So if you want to subtract, you do the multiplication by minus. But there is no formally in linear space operation where you multiply one vector by another. Okay, so you probably remember from either high school or like some analytical geometry, like there's a vector multiplication cross product, but that's not always exist in all the spaces. Like it exists in 3D, but you go to 4D and it doesn't work there. Or in quantum mechanics, there is no definition of like how do you do the cross product of two functions. So, but that's a step into the direction of what is formally known as algebras in abstract algebra. Algebras, they are linear spaces with an extra operation of vector-vector multiplication. And another thing not to confuse is that when I talked about a vector-vector multiplication, I'm talking about the operation that produces, again, vectors, right? So linear combination, or like, since we're in linear space, any linear combination of vectors is vectors, right? So we are getting the vector as a result, and this is very different from what you know as an inner product, right? When inner product happens, you get the number, right? So with that, usually we have in any linear space equipped with inner product, but in algebras, we need the vector times vector. And why am I talking about this in the case of operators? Well, another thing that sometimes not clearly articulated, but it's important thing to say is that the whole in quantum mechanics and even in the, I guess, linear algebra as a kind of a branch of math that you study usually relatively early, the whole really name of linear algebra is not related to sort of vectors in normal sense of like pointing arrows, right? The vectors that, of course, the subject of linear algebra, but linear algebra is the name that is coming from actually the algebra of matrices, okay? So because matrices, if you have M1 plus M2, matrices could be considered as vectors in this abstract sense, because you can multiply any matrix by a number and add another matrix multiplied by a number, is still, if they're the same dimension, right? So they are forming linear space. And as opposed to like vectors in the sense of like this functions or pointy arrows, matrices, there is a way to multiply them, right? So if we multiply two matrices, we get the third matrix, right? In that sense, it is algebra because we take one vector, multiply by another vector, and get the vector in that linear space sense, okay? So that's why the word linear algebra really is the algebra of linear objects, but it's about all objects of matrices rather than objects of the I guess the vectors there also is like a columns or arrows. There's also matrices, but they're not kind of matrices that are easily multipliable in the using this matrix algebra multiplication. But this is kind of coming to the algebra of these operators. What here is done is that if you look at the A dagger and the A as vectors in the linear space, then these anti-commutators, they are ways to multiply, right? Because what it produces is actually another vectors of that same space, and so that construction in particular case is called Clifford algebras. We will talk more about them, but Clifford algebras, the specific case. What is nice because about this Clifford algebra is that these anti-commutators allow you to sort of reduce the complexity, right? Because think of if you have a product of two operators, if you have this anti-symmetric product, then you could get rid of the operators essentially. And if you will be able to find in the linear combination of some products the places where they come in anti-symmetric pairs, then it could simplify things. All right, that's one reason why we care about that. Okay, and then I guess one of the last points on the second quantized formalism is that we need to represent the Hamiltonian eventually, because that's the object that we want to solve eigenvalue problem for. And in order to do that, we need the representation in terms of what was promised, creation and negation operators for the 1 electron and 2 electron operators. Okay, so for 1 electron, any 1 electron operator, if xi is a 1 electron coordinate, sometimes xi, what it means is the ri and the spin variable for the electron, right? So any 1 electron operator in the first quantization can be written like this. And then it turns out that we could consider every term in this sum because, well, in first quantization, all the electrons are kind of indistinguishable. So supposedly the right operator needs to act the same way on all electrons, right? And then in the second quantization, what will happen is that each term, what it will do, if you think about it, so if there is a function of a particular electronic coordinate, then what it can connect this function in terms of Slater determinants, right? So if we think about the matrix elements between the two Slater determinants, so since we are working in the orthogonal basis of spin orbitals, so then it turns out as we looked at the without this thing, these two will give you 0 if the spin orbits of this one will be different than spin orbits of this one, meaning that populations will be different, right? But if we include a single electron term like this, then it is allowed to like this two spin Slater determinants allowed to have one pair of spin orbits which are different. Let's say this one is has a kind of occupation on the first one and no occupation on the second, and this one say on the second but not on the first, right? So they are allowed to have one spin orbit difference. And I know this kind of a little bit maybe hand-wavy explanation. The formal way of deriving all this for one electron and two electron operators is called Condon-Slater rules. Condon-Slater rules. They are considered in any electronic structure book. So if you are not aware of them, please take a look, right? Because many things rely on them, and this is one of them. That for any single electron operator, then in a second quantization, because the first quantization version only connects the things with the difference by one orbital, then the second quantized form also will have only one excitation inside, right? So A dagger P, A Q. And then the only thing that is left is just to connect the coefficients in front of the these excitations with the function of the coordinates. And that connection, again, you could look at the Hilgacker's book where it's done. It could be easily written like this as a so-called one electron integral, where we take the function of a single electron and integrate it with the functions that we've chosen for spin orbitals. And these functions, these integrals may not be analytic, but since it's for like at least one particle, so that means it's a three-dimensional spatial integral plus spin variable, but these are considered to be easy to calculate on a classical computer. You could do it in polynomial sort of complexity. And then if your orbitals, spin orbitals are real, then FPQ is the same as FQP because the conjugation here doesn't really change anything for real spin orbits. The same kind of idea could be applied for the two electron operators, right? And exactly the same way for the two electron operators. Now this Slater determinants could be different by two orbitals, spin orbitals, right? That's why we have two excitations, two excitations, right? So the two creation and two annihilation operators, and then to match the coefficients to the integrals, the expressions like this will appear. Now, if you look at this expression for the real spin orbitals, you of course can exchange P and Q, R and S, and then you could do the combination of those together, separate, right? But in the electronic structure theory, where our two electron integrals are the Coulomb interaction, right? So we have this G12 is the same as G21, and because of that extra symmetry, there is yet another equality here where we can essentially, what is one more symmetry? Is the one that essentially exchanges the first particle with the second particle, because the G doesn't really distinguish them. Right? And so in total, we have 8-fold symmetry for the two electron integrals, because we usually work with the real orbitals. Okay, so that concludes the sort of a second quantization formalism really quickly review. And so what did we get? We get states that are a linear combination of Slater determinants, and we got some expressions for our Hamiltonian as a operator written first, second, first 1 electron, 2 electron parts. And the main gain is that we have this now expression of the operator in terms of algebraic, nice algebraic operators with the rich algebra, Clifford algebra, and with this anti-commutativity conditions, right? And if this at this point probably sounds a little bit abstract, like what do we get? We're going to get out of this Clifford algebra condition. It's not clear, but one thing to realize is that in the first quantization, if you think about the Hamiltonian, then the representation of the Hamiltonian is like in the coordinate space. Technically, it's coordinate space is essentially infinite. You could think of it as an infinite matrix, but in terms of any finite basis, the Hamiltonian, in order to exactly represent it in the finite basis, you will require exponentially large matrix. So what is nice about second quantized form of the Hamiltonian, it's a polynomial form written not with commuting operators, but anti-commuting operators. All right, so it is exact within the finite basis, and it is polynomial. So that is much nicer qualities than having exponentially large matrix to work with. Okay, that's what makes the second quantization convenient for the manipulations. Okay, and then the cost of that is that we shouldn't forget that we now have more states because of the Fock space. And here's the simple example. If you use STO3G, this is a like simple atomic basis for taking one particle functions, hydrogen. So we have occupied sigma, unoccupied sigma star, right? And so those are the typical configurations you may think about, right? And in this case, but in the Fock space, there are more states. There are states of 1 electron, 4 electrons. There are states of different spin, right? And even vacuum is yet another state with no electrons. So we have all the states, and right now we see that these states could be easily separated, but turns out when we go to the qubit space, that will not be as obvious because we will map these states to the states of qubits, and we will have the same number of qubits for all the states, and it creates some interesting challenges. This fact that we're working now with the bigger space. Okay, we should not forget about that. All right, so now, yes, in the last half an hour, I will start the Fermion qubit mapping. That's where essentially we are trying to, in order to get to the quantum computer, we need to formulate the states and the operators in terms of qubits. And this is probably my favorite paper on that subject by Peter Love. It's a very pedagogical paper on complicated transformation, which is Bravin-Kitaev transformation. I'm not going to go over that transformation. I instead will talk more about the very kind of one of the first transformations between the fermions and qubits, Jordan-Wigner transformation, which is done in 1928, right? Because it's just simpler to understand. Now, Bravin-Kitaev's work explained very well in the Peter's last paper, but has some advantages which are not very relevant to the near-term algorithms. they are more relevant to the probably fault-tolerant algorithms. You could look at the Peter Love's paper for details, but the title is Bravik-Kitaev, so that's why Bravik-Kitaev sort of popped up in the beginning. But let's see. Yeah, motivation is clear. We want to get to the qubits, and for that we need to essentially transform our wave functional operators, right? And yeah, as we were talking before, solution for our Schrödinger equation now in the second quantization is just a linear combination of this binary kind of binary lines that encodes later determinants. Technically, one can say it's 2 to the n, where n, change in notation here, is now number of spin orbitals, right? So we have this kind of wave function, and why qubits are coming to mind, why we have a hope to describe the same solution using qubits, is because, well, if you never heard about qubits, it's just two-level systems, and they are represented well with these pointy arrows on the block sphere. But you could also think about them. We're not going to go into the details of how they implement it because it's hardware stuff. But you could think of them as a spin of electrons if you want. But only the case is that we are dealing with distinguishable qubits, right? So they're distinguishable particles. And so then naturally for spin of electrons, you have up and down states. And then that very naturally encodes zeros and ones, right? So you could take the zeros and one product states and represent them up and down kind of spin orientations or qubits, because qubits are essentially two-level systems. For all our purposes, it's two-level system where either this state is occupied or this state is occupied, right? So we have 0 and 1, if you want, or this could be up and this could be down. And we could create any superposition, which you probably heard about a lot these days, that we could create a superposition, or that sometimes they're compared with Schrödinger's cat, dead and alive, all that sort of stuff. But this is a qubit state. And of course, in these coefficients, you can store the information technically, right? But a single qubit is not as powerful as multiple qubits, and we'll talk about this phenomenon more. What makes the multiple qubit case more powerful is that we can use entanglement, which is essentially storing information in linear coefficients, in front of the products of the states, right? And the fact that this linear combination cannot be written as simply a product of, let's say, a alpha, like let's say 0 or I qubit 1, or the I qubit vector I, right? So products over I. So the fact that it's not just simply a product makes it very powerful, because for the product we would have, if it's n qubits, it's only 2 times n minus normalization condition, right? So we have something like this, number of parameters that we can play with. But if we have really all possible product states with the coefficients, then the number of parameters grows the same way as the number of products, which is exponential. Okay, and so then for n qubits, we can have 2 to the n complex numbers that we could use to encode our wave function. So that's 2 to the n, kind of corresponds to the 2 to the n that we started with in the Fock space. And that gives us hope that using n qubits, you could describe the system with n spin orbits, right? But this is just a hope in the beginning. And I also want to always say that this is if someone gives you a solution, you could write it down using qubits. But there are also quantum algorithms you need in order to generate that solution, right? But that's a good start, at least, that you have a place to put it if you generate it, okay? Right, and then the current technology, I guess, allows us to put quite a bit of information for a very short time. Because, yeah, I guess the IBM is quite ahead of Google right now, and has already a couple of hundreds of these qubits. But there are some still problems that you cannot keep these qubits in this entangled state for long, right? And so if you do manipulations with information, which we usually do in quantum computer, then it's becoming a challenge to use all that information and not to spoil it, because there is like a aggressive environment essentially that generating noise and errors in our media, right? So that's the current challenges. All right. So what I wanted to, I guess I won't be able to finish this today, but what I want to start is somewhat describe some again, like in the second quantization, we want to make ourselves somewhat comfortable with the states of qubits and single and multiple, and also operators that we use in the qubit land, sort of speaking. All right, and we start with a single qubit. How do we think about this system? What are the operators for a single qubit? And then we'll go to the multiple qubits. Okay, so for a single qubit, as I was showing here, it's a two-level system. Could be in superposition, always alpha up plus beta down. It's a state of single qubit. And because these are complex parameters, like in quantum mechanics in general, so they, and this is a physical wave function, then we have a normalization condition. Okay, and then this could be written using the sort of real and imaginary parts. This is essentially without absolute squares already, alpha r plus alpha imaginary squared plus and then the same for beta. Okay, so beta r is beta squared, right, it's equal to 1. So this is a geometrically condition for the three-dimensional sphere in the four-dimensional space, right? So this is a way you could think about this, the degrees of freedoms. But then you realize that the overall phase doesn't really matter for anything, and therefore actually this 3D sphere in a 4D space, sphere could be reduced to just a 2D sphere in the 3D space. And that sphere is sometimes called block sphere to describe the state of the qubit that is encoded in these coefficients, which are complex in general. So how do we really get to this?
You can pull them.
Oh yeah, right. yeah, so to get rid of this extra phase and see clearly the block sphere structure, one can just simply use alpha polar notation I phi, but is R E I, sorry, notes that phi, right? So have this, and also we have a condition that R squared plus phi squared, rho squared is 1. Simply again because alpha squared and beta squared is 1, and these are just the phase factors, right? Now, if we write the qubit state as this notation, rho ei theta 0 state plus r I phi state 1, then we can get the overall phase out, say I phi, and inside will be rho theta phi, the difference. Okay. And then let's say we use the theta minus phi identity. Let's call it delta, and this is going to be cosine delta plus I sine delta. And the fact that r squared plus rho squared is 1 essentially allows us to say that we can call r some cosine of some angle. Let's call it chi, and then rho will be a sine of that angle. So sum of squares is 1 for cosine and sine, right? And so then this whole thing will be the general phase, and then sine of chi, and this will give us cosine delta plus I sine delta y by 0 plus sine chi 1. Okay, so if we ignore this overall phase, then what we have here is really spherical coordinates, because it's like a cosine, sine, and sine, two sines, and the sine and cosine, right? So this, of course, are different because one is with I, another without I, and that's why you could think of this as a point on the sphere that is described using the spherical coordinates. If you ignore this overall phase. That's the block sphere representation of a state of a qubit. Then we now can talk about the sort of operators that we usually use for manipulative qubits, right? So down, and any operator that I guess O that works on a single qubit, one qubit, can be written as a linear combination of well, if it's a, I guess, a general one qubit operator, it's always going to be I guess, Hermitian part, qubit Hermitian part, plus anti-Hermitian part. And then for, well, this Hermitian and anti-Hermitian parts, for one qubit or any other operator, it's just O plus minus O dagger divided by 2 qubit, 1 qubit, right? And then for the Hermitian part, I guess Hermitian and anti-Hermitian doesn't matter. What we can do is we can always say this is a sum over coefficients, Ci, I goes from 0 to 3, and then sigma I, where sigmas are Pauli matrices. Okay, so sigma 0 is identity. Sigma 1 is also known as sigma x 0, 1, 1, 0. Sigma 2, sigma y 0 minus I 0. And then sigma z also, okay. Sigma 3, sigma z 1 minus 1 0 0. Okay, so now for the Hermitian part, these are real coefficients, and for anti-Hermitian part, these coefficients are imaginary. Okay, so you could easily check that all this, sometimes put the hats, sometimes skip them. So for these Pauli matrices, you could see that they have a very many nice properties, and we'll be using them a lot. So they also turns out to form Lie algebras and Clifford algebras. So there are lots of nice things we can say about them. But one thing that kind of almost obvious is that they're all Hermitian. So any sigma q Hermit conjugated is this, right? They're all Hermitian, and also they are unitary. Sort of the sigma q star sigma q identity, but because they're also Hermitian, they are sometimes called self-inverse. So sigma q gives you identity, which is also the same as sigma 0, right? So I sometimes use sigma 0, sometimes identity. Let me know if yeah, it's not clear. But this is another nice property that also called involution. So if the operator squared equals identity, it's an involutory operator. And why is it nice? Because, well, it will be very handy in, let's say, putting some functions of the operator. Let's say exponential functions sometimes appear, right? And if you generally take the exponential function of some operator, then you need to deal with the whole Taylor series, right? Which is infinite. But if you have this property, then it turns out the only powers of sigma that you need is just a linear, like a first power, right? Because the square is over the identity, and identity is already the 0 power, right? So then any function like this, which is usually, to make it unitary, it's I theta sigma q, where theta is some angle. So then you get the expressions like this: I sine theta sigma q. So all the odd powers, they collapse to this term, and all the even powers here multiplied by identity collapse to this, right? So cosine takes everything that is of the even power and the sine of the odd powers, right? So that's a nice property then of the operators that will be useful. Then what else do we have? There are commutativity relations. That's why they form Lie algebra. So sigma, like that you probably know from the basic quantum mechanics, sigma x, sigma y equals 2I sigma z. And then you could make all sorts of rotations, meaning that z goes to instead of x goes instead of y, and y goes here, right? So you can generate all three commutativity relations. And by taking any of the sigma matrices, you are not going to get anything but sigma matrices. That's why they are kind of closed with respect to commutativity. Okay, and that's one reason why it's called Lie algebras, is because this, if you think about this as a vector and this as a vector, so, and this is vector-vector product, it produces another vector from the same set, okay? And so as you can see, these vectors are useful to describe other operators, right? So you decompose any vector, which is an operator, in terms of these basis vectors, right? And that's why mathematicians, they call it SU2, Lie algebra. Lie algebras generally is like a set of operators or vectors, you could think of them, that if you do the commutations, they give you back the same stuff that you already have in the set, right? Could be linear combination. In this particular case, it's very simple. So it's the nicest non-commutativity in general, because we know that why we like commutativity, because the operators that commute, we can obtain eigenstates for all of them at the same time. The ones that don't commute, we can't, but and things become more complicated with them. But if they don't commute in this nice way that they don't produce more and more stuff when they don't commute, then there are kind of simplifications one can make, and we'll talk about them more. Now, this code name is essentially U for special unitary, and the special 2 is just a dimension. And the special thing about them is that they're all traceless. That's property number 4. Trace of sigma q is 0. And this is also somewhat related to the involution, because you could show that if the operator that you square in always gives you identity, and it comes also related to Hermitistic and unitarity. Long story short, all the eigenvalues of all these operators is plus minus 1. Okay, so then clearly trace is a sum of plus 1 and minus 1 and 0. That's what we have. Another property 5 is that they anti-commute. So any sigma x, generally speaking, sigma q prime, anti-commutator with well, gives 0, where q and q prime are only 1 to 3. So all the ones that are not trivial, like sigma x, sigma y, sigma z, they all anti-commute with each other. Okay, and that's a nice connection with fermionic operators, which can be exploited later. Okay, I guess I'm at the end of my presentation, and we will start talking about the multi-qubit operators, and we'll finish the mapping next time. Okay. Any questions? People online?
It's just the last one, the Q and Q prime. must be different, right?
That's correct. Yes. Yeah. Thank you for noting that. Yeah. So this formula is if they are the same, then it gives you two, yeah, delta q prime, right? So yeah, for the same case, you get the identity. All right. Okay. I see you next time then.